Dear audience, in this video, I'm going to present my recent work titled Entanglement Dynamics from Random Product States at Long Times. My name is Yicheng Huang, and I'm from Center for Theoretical Physics at Massachusetts Institute of Technology. My background is in quantum information theory and condensed matter physics. Abstract. We studied the entanglement dynamics of quantum many-body systems at long times. Here, a quantum many-body system, you can just imagine that you have a system of many qubits. Our results can be in different settings. The first setting is that we have a geometric local Hamiltonian on a lattice. Geometric local here means that each term in the Hamiltonian acts on a constant number of qubits that are close to each other on the lattice. We initialize the system in a random product state and let it evolve under the Hamiltonian. We can prove that the entanglement entropy almost never approaches a page curve. Page curve here means that refers to the entanglement of a completely random state in the entire Hilbert space. And as we will see later, the entanglement of a random state is almost maximal. We could also consider the setting that we have a spin glass model with random multiple interactions. In this case, we do not require that the initial state is a random product state. It could be any product state. And we can show that the average entanglement entropy doesn't approach the page curve. Here, the average is with respect to the randomness in the Hamiltonian. We can extend these results to two other settings, including unitary evolution with charge conservation. Here, the unitary evolution doesn't have to be generated by a time-independent Hamiltonian. It could be any unitary evolution, for instance, a quantum circuit. As long as we have charge conservation, then we can prove a similar result. And we can extend the result to the Such-Kitaev model, which is a model of Majorana fermions with random multiple interactions. And this is a model that is maximally chaotic in some sense. The main conceptual message of this work is to highlight the difference between the entanglement generated by chaotic Hamiltonian dynamics and the entanglement of random states. For time-independent Hamiltonian dynamics, we have energy conservation, and this conservation law prevents the entanglement to reach the maximum value, and this is the intuition. Before presenting the technical results, let me define the setting. We start with a definition of the random product state, hard random product state. So we have a system of n spins and have a product state, and it is hard random if each individual the state for each individual spin is chosen independently and uniformly at random with respect to the Haar measure. That is, the state vector is distributed uniformly on the block sphere. For a hard random product state, we can prove that it is a massive superposition of energy eigenstates. That is, if suppose you have a Hamiltonian and you get the energy eigenstate, and you can expand the hard random product states as a superposition in these spaces. And by massive, I mean that many of the coefficients in this superposition cannot be, many of the coefficients are non-negligible, so that many of the energy eigenstates participate in this superposition. The time evolution under a chaotic local Hamiltonian is so complex that heuristically one might expect that the state at long times behaves like a random state. So this leads to the following conjecture. That is, for chaotic, not necessarily geometrically local Hamiltonians, starting from a hard random product state, the entanglement entropy approaches the page curve at long times. Here, page curve is just the entanglement of a random state, and the goal of this work is to examine to which extent this conjecture is true. Now let us review page curve. We start with the definition of entanglement entropy. First, we have a bipartite pure state rho AB, and we can compute the reduced density matrix and the entanglement entropy of the bipartite pure state is defined as the Von-Neumann entropy of the reduced density matrix. Then we could choose a bipartite pure state uniformly at random with respect to the Hahn measure in the Hilbert space. Then what is the average entanglement entropy? This problem was first studied by Page, and the result is given by equation 1. Here we have two subsystems A and B, and we define the size of a subsystem as the number of qubits in the subsystem. So the total system is a system of many qubits, and dA and dB are the dimension of the Hilbert space for subsystems A and B, so that dA and dB are exponential in the size of A and B, respectively. So that imagine that size of subsystem A is a constant fraction of system size with a constant less than 1/2. Then we see that dA over dB is exponentially small in the system size. So that in this case, the entanglement entropy, the average entanglement entropy of random state is almost maximal log dA minus a quantity that is exponentially small in the system size. That is, in summary, if we consider the entanglement of random states, and if the smaller subsystem is a constant fraction of the system size with a constant less than 1/2, then the average entanglement is almost maximum, up to exponentially small quantity. We are ready to present our first results. Is about geometric local Hamiltonian. Consider a chain of capital N qubits governed by a local Hamiltonian, such in which each term acts on neighboring strings, and we do not assume translation invariance. And we need to specify how to get subsystems, and we just consider all contiguous subsystems of size and use this notation to denote their average. There are capital N such subsystems because we use periodic boundary condition. Then our main theorem is that we initialize the system in a hard random product, say capital psi, and let the rho AT be the reduced density matrix at time t for the subsystem A. And our result is that if the size of the subsystem little n is larger than 1, then we have equation 2. Let me explain what it means. As rho AT is entanglement entropy, we average over subsystems and take T to be the 1 such that the entanglement entropy is the largest. We see the probability of the following event. That is, the entanglement entropy is equal to the maximum entanglement minus little o of little n over capital N. So assuming that little n is a constant fraction of capital N, then this is a little o1. So the event in the big parenthesis just means that the entanglement entropy approaches the maximum entanglement in the limits that the system size capital N goes to infinity. Then what is the probability? The probability is a little o1, means that the probability just vanishes in the thermodynamic limit. In other words, equation 2 just means that if we randomly pick up a capital psi, then with high probability, the entanglement entropy will be is upper bounded by the maximum entanglement minus a constant. So that this is different from the Page curve, which says that it is maximum entanglement up to an exponentially small correction, as long as little o over capital N is a constant less than 1/2. So this is our first result. Let me mention that this similar result holds for qubits in higher spatial dimensions, and the proof is almost identical. I don't have time to go into the proof, but the proof relies on the energy conservation of the time evolution. So the question might be, the next question is that if we do not have energy conservation, but have other conservation laws for others, then whether we have a similar result. The answer depends on what conservation you have. For instance, if you just have Z2 symmetry, then this is not very helpful. But if you have other symmetry like charge conservation, then a similar result can be established. In particular, in this case, we consider a system of capital N qubits without an underlying lattice structure. And we specify how we get subsystems. We consider little m, this number of subsystems. And each subsystem has exactly little n qubits. So little n is the subsystem size, and capital N is the system size. Furthermore, we require that each qubit appears in the same number of subsystems. That is, each qubit appears in little m times little n over capital N out of these m subsystems. And with this setup, we proceed by defining the total charge operator. This is just a sum of sigma z. Sigma z is a Pauli z matrix. And let UT be the time evolution operator. And the only requirement for UT is that it commutes with the total charge operator. Then we can get a similar result. That is, we initialize the system in a hard random product state capital psi. And the rho AJT is the reduced density matrix of subsystem AJ at time t. Then we have a result given by equation 3. This is very similar to what you have seen before. This time we average over these m subsystems. Next, we consider a model with random O2O interactions. This is a spin gas model. In this model, we have a system of n qubits, and these are the Pauli matrices. And the Hamiltonian is given by equation 5, and it involves all types of two-body interactions. Here, JK are the indices for the spins or qubits, and the LM are XYZ index. And we have all combinations, and we collect the coefficient. The coefficient is called the J sub JKLM. And this is a random number. It is an independent standard normal random variable. And we collect all these random variables to be capital J, so that the Hamiltonian itself is, the model itself is an ensemble of Hamiltonians, or we can view the Hamiltonian to be random, and each J corresponds to random sampling. And we consider all subsystems of sites and let this notation denotes averaging over all subsystems of sites, and there are capital N choose little n such subsystems. And our result is the following. We start with an arbitrary deterministic product state called psi, and for each sample J, we evolve the states under the Hamiltonian, and up to time t. Time t can depend on the sample you choose. And we have rho JA. J refers to a sampling of the Hamiltonian, and A is the subsystem. And then we have for the subsystem size larger than 1, we have equation 7, which says that this is the entanglement entropy and average over subsystems and choose time t such that this is maximal. And then we average over randomness denoted by J. What we get is that it is equal to n log 2 maximum entanglement minus omega of little n square over capital N square. So that if little n is a constant fraction of capital N, this is a constant, this is at least a constant smaller than maximum entanglement. And this is different from the page curve if little n over capital N is a constant less than 1/2. Finally, let me present the result for the SYK model, which is a model of Majorana fermions. We have n capital N Majorana fermions. Capital N must be an even number in order to make sense. And the Hamiltonian is given by equation 8. This is a Hamiltonian that involves all 4-body interactions. And this is anti-commutation relation for the fermion, Majorana fermions, and the K sub JKLM is an independent standard normal random variable. And we could also collect these random variables into capital K. So capital K is refers to a sample of the Hamiltonian. And let this symbol denotes averaging over all subsystems of size. And here little n also must be even in order to make sense. And there are capital N choose little n such subsystems. But before presenting our results for the Syk model, we need to mention a subtlety. That is, in fermionic systems, defining a hard random product state is tricky. This is because of the following. The Hamiltonian preserves fermion parity, so that the Hilbert space is split into an even sector and an odd sector. And these two sectors do not interact with each other. So it is controversial whether we should allow the superposition of states from both sectors. We should mention that such a superposition is compatible with the axioms of quantum mechanics, so that in principle, it seems that it should be allowed. But on the other hand, such a superposition is widely believed to be unphysical. We are not we need to mention that if we require to have a definite fermion parity, then it is not straightforward to define a hard random product state. So our results, that is a theorem presented in the next slide, avoids this controversy and related technical issues by introducing a condition for the state psi instead of claiming it to be a hard random product state. So what is the condition? The condition is given by equation 9, which says that the expectation value of Kij, Kk, Kl, Km with respect to psi is order 1 quantity for a constant fraction of the tubes JKLM. So why this is reasonable? Recall that in spin systems or qubit systems, hard random product state has a property that its local reduced density matrices deviate from the maximum mixed state, that deviates from a state that is proportional to, whose density matrix is proportional to I in a random sense and by an order 1 amount. And if we assume that the local reduced density matrices of the state psi also deviates from the maximum mixed state by an order 1 amount, then we have equation 9. This is because the expectation value of Kj, Kk, Kl, Km with respect to maximum mixed state is exactly 0. So that if the local reduced density matrices deviate from the maximum mixed state by an order 1 amount, then we expect that the expectation value also deviates by order 1, deviates from 0 by order 1 amount. In this sense, we have equation condition 9. And with this condition, we get a result that is almost the same as the result for the spin glass model. That is, you have the entanglement is given by n log 2 over 2 minus omega of n to the 4th power, little n to the 4th power over capital N to the 4th power. We have log 2 over 2 because our system is a Majorana fermion system. And if little n is a constant fraction of capital N, then the correction is at least a constant. We are ready to summarize the results in this talk. We studied the entanglement dynamics of quantum many-body systems at long times and consider different settings. The first setting is that we have a geometric local Hamiltonian on a lattice. Then, if the initial state, the random product state, the entanglement entropy almost never approaches the page curve. And the second setting is a spin glass model with random all-to-all interactions. Starting from any product state, the average entanglement entropy doesn't approach the page curve. We can extend these results to any unitary evolution with charge conservation and to the such depth F model. The main conceptual message is that our results highlight the difference between the entanglement generated by a chaotic Hamiltonian dynamics and that of random states.